Composers have always arranged and rearranged their music until it has just the feeling or structure they desire. And the product of their creative effort, a melody or harmony, must be preserved so that other musicians in the future can perform it again. Today's musicians, like Fred Haas, command a new kind of tool to record everything they've played. It's not a tape recorder, but a digital computer. In this case, part of the Synclavier digital audio system. As we'll see, the Synclavier is a powerful device with many capabilities. Preserving a composition is just one of them. At one time, this much computing power would have occupied even more space than the small section of the 1950s air defense computer behind me. Now on display at the Computer Museum in Boston, this IBM Q7 tracked enemy aircraft until 1983. Now, radar blips in modern music seem very different, but the Q7 and the Synclavier do have one essential element in common. They both receive, process, and reproduce information. A computer doesn't understand radar or music directly. Its ability to deal with information is based on coding. In fact, everything computers do depends on codes that represent information. Codes are the mechanisms we need to store and make use of all information. The alphabet, for example, is a code of 26 symbols that we use to preserve our fleeting speech in written form. And long before we were around, nature developed a biological coding scheme. Chemical patterns that make up DNA are called the genetic code. Recognizing that codes can represent information is an important insight that comes from mathematics. In a sense, all mathematics exploits this idea. For example, we can represent things in the real world with equations, a code of numbers and symbols, which we then manipulate to find results that can be applied back in the real world. In mathematics, a code consists of two elements, a group of discrete symbols and a set of rules for interpreting those symbols. In music, those same elements make up a code called a score, and it can help us understand the codes that run computers. The basic musical symbol is the note like this one. Of course, there are other symbols, such as this note here, which signifies a longer duration of the sound. But just look at this symbol, sort of a black blob on a stick. How does a performer know to play this or this? How can a code with just one symbol encode so many different sounds? In other words, what are the rules of interpretation? The answer, of course, is that the information encoded by the note varies according to its location on the staff. Mathematicians refer to encoding systems like this as place value systems because the value of the symbol is determined by its position. A note here means play this, while a note here means play this, and the same symbol over here means play this. We all use another place value system every time we look at numbers. There's no mystery to the difference between 2 and 20. We've learned to recognize, without thinking about it, that the symbol 2 in this place means 2 ones, and that the same symbol here means 2 tens. In music, the same principle allows a trained performer to quickly recognize the values of the notes. What note to play is encoded by the note symbol and the place value system of the staff. Those same elements show up here on a player piano roll. But this roll adds a new capability to the music code, something the score alone could not do. This music can be performed mechanically by a machine. Even after radio and phonographs and now CDs, Americans still buy long paper rolls of their favorite music. It's because tens of thousands of songs can be enjoyed in a way not possible with those more modern media.
The beauty of this thing is, of course, that when the consumer plays the roll, he's getting the actual performance on an instrument in his home. And I can't think of any higher kind of fidelity than that.
Of course, the titles have kept up with current tastes, but then that's been the goal at QRS Music Rolls in Buffalo, New York, since the turn of the century.
People tend to identify the player piano with the 20s because it was very, very popular in the 20s. But the fact of the matter is it's really a timeless instrument. It is really nothing much more than a piano that plays itself. And it is because of the way that the music is encoded on the rolls that we have the capacity for a timeless performance. Basically, it's a pneumatic device, atmosphere rushes in through the holes in the paper and activates a series of valves which strike the keys. The 88-note roll plays all 88 notes on the piano keyboard. The lowest notes are represented in the paper by perforations at the extreme left. The highest notes are represented by perforations on the extreme right-hand end of the roll. And the duration of the note depends on the length of the perforation.
All those holes must be punched at a snail's pace with his arranging piano. Most of this music is encoded by staff arranger Rudy Martin onto master paper rolls.
Now, to make it sound correct and in tempo, what you have to do is, according to the musical values of the notes, I assign a certain amount of punches. For example, 12 punches for one beat or quarter note. 2 beats will be 24, 3 beats will be 36, and so on. So then what I do is I turn this machine on and show you how it operates. So what I do is I punch and count mentally. It's all done mathematically.
In the factory, the pattern of holes from the master is copied to many rolls at once. Each maintains the precise musical value of the notes. Player pianos simply interpret a hole to mean play and the lack of a hole to mean don't play. For nearly a century, just 2 symbols have filled millions of homes with actual performances on real live pianos. Like the play or don't play code of the player piano, computers also run on just 2 symbols, which can be stored on a floppy disk, for example. Each tiny area on the magnetic surface is polarized by electric current into just 2 states, either north or south. Such a simple and unambiguous representation was crucial to the development of computers as 2-symbol machines. As so often happens, the mathematics needed to exploit these characteristics of electricity and magnetism was developed long before modern computers were a practical possibility. The key is a scheme for representing numbers with only 2 symbols, the binary system. Now, how can a code with just 2 symbols represent all the information that computers process? The answer comes from combining the 2 ideas we've looked at so far: a 2-symbol code interpreted by means of a place value system. Remember that a single note symbol can serve to encode all musical sounds, thanks to the places created by the staff. And in decimal numbers, place value distinguishes units from tens, tens from hundreds, and so on. In binary, the 2 symbols we use are 0 and 1. To see how place value works in binary, imagine we've just bought a new high-tech car with 2 odometers. The top odometer is a decimal counter, while the bottom one is binary. As we count up from 0 through 1, the displays are identical, but there's no single symbol for 2 in binary. Instead, we begin a new column. This number, which is read as 10 in binary, is equal to 2 in decimal. The second binary column, in other words, keeps track of how many 2s we have. When we get to 4 in decimal, we've exhausted all the binary symbols in 2 columns, and we have to begin another. The third column in binary represents how many 4s are contained in the number. The symbols 0 and 1 are called binary digits, or bits for short. So we can say that the number 4 in decimal requires 3 bits in its binary representation. As we jump up to higher numbers, we can see the place value pattern. Each column represents a new power of 2, 0, 1, 2, 3, 4, and up, the equivalent of 1, 2, 4, 8, and so on in decimal. Each power of 2 requires 1 more bit in the binary representation. It might appear that strings of bits are an awfully inefficient way to encode a large number, at least in terms of the number of places required. But remember that a 2-symbol code is ideally suited to magnetic storage devices like floppy disks, and new technology keeps increasing the storage capacity while decreasing the cost. There's another reason why the binary code serves computers so well. The story begins 100 years before early computers such as the UNIVAC, back in the 1850s with the English logician George Boole. Boole's ambitious goal was to codify the laws of thought. He studied the ways we draw logical conclusions from different combinations of statements. Now, statements can be about anything at all. Say, for example, that statement A is, the balloon is red, and statement B is the balloon has polka dots. A is true for this balloon, but false for this one. Boole's innovation was to create an algebra, a mathematical approach to the logic of statements. He assigned 0 to represent false and 1 to represent true. So statement A, the balloon is red, has the value 1 for this balloon and the value 0 for this one. Now, let's consider the two statements together. We can describe the possible combinations in a table. Remember, 0 means that the statement is false, 1 that it's true. What about the compound statement A and B? In terms of our example, this says the balloon is red and has polka dots. We want A and B to be true to have the value 1 only when both A is true and B is true. We can summarize the information about this combined statement by turning our original table into a so-called truth table. This truth table transforms our intuitive notion of AND into a mathematically precise definition. A and B is true only if the balloon is red and has dots. The relationship AND is one of the ways compound statements are built in logic. Technically speaking, AND is one of the logic functions. More than 80 years after Boole's time, in the late 1930s, a similar inspiration occurred to a number of men who were working toward automated calculating machines. In this country, that insight struck both Claude Shannon, a master's degree candidate at MIT, and George Stibitz, a mathematician at Bell Labs. These men and others realized that Boole's algebra of logic could be physically embodied in electrical circuits. The circuits engineers used in the 1930s were relay switches, which are like light switches turned on and off by electromagnets. These two positions allow current to either flow or not flow. Therefore, on or off can represent two values, say 1 and 0. Now, we've already seen that the truth value of statements can also be represented by 1 and 0. Shannon and Stibitz's breakthrough was to recognize this parallelism and to show that circuits could represent relationships between statements. So let's return to our statements A and B, which are either true or false. That is, have truth value 1 or 0. Now think of A and B as representing two relay switches in a circuit. Then the logical function A and B can be represented in a circuit diagram. If current is flowing in both A and B, then this AND circuit permits current to flow, otherwise not. Of course, in a modern computer, this circuit is represented by a tiny intersection on a microchip. It's called an AND gate, and it's represented this way in the diagrams used by electrical engineers. There are a number of logical functions fundamental both to Boolean algebra and to the design of computers. Another useful one is called the exclusive OR relationship, abbreviated XOR. This truth table defines the function A XOR B is true if either A is true or B is true, but false if both A and B are true. Again, we can build a circuit to carry out this function. An XOR circuit is represented by this engineering symbol. To see how these logic functions and the circuits built for them make it possible for a computer to do arithmetic, we need to take a minute to establish the rules of binary addition. Fortunately, they couldn't be simpler. There are only 4 possible pairs of digits. The sums for each pair are 0, 1, 1, and 1, 0. This last case is the most interesting. When we add 1 plus 1, we get a sum of 0 and a carry of 1. You'll remember that 1, 0 is the way decimal 2 is represented in binary. Now we're ready to build a circuit that adds. To show you how it's done, we'll construct the simplest possible version, the so-called half adder. This circuit has 2 inputs, 2 binary numbers, each 1 bit long, and 2 outputs, a sum bit and a carry bit. The possible values of inputs A and B, with the resulting sums and carries, are listed in this table. The sum and carry values express the same information we saw in our glimpse of binary arithmetic. And the half-adder circuit requires just two logical elements, the AND gate and the XOR gate. Remember how the XOR gate works, and you'll see how it fulfills the sum function. XOR outputs a sum of 1 if A is 1 or if B is 1. If both inputs are 1 or both are 0, XOR outputs a sum bit of 0. The AND gate takes care of the carry bit. Only if A and B are both 1 does the AND gate output a 1. Otherwise, it outputs a 0. Together in the half-adder, therefore, the AND gate and XOR gate correctly perform binary addition for two single-bit numbers. If you build in the ability to receive carry bits from previous calculations, you have a full adder circuit for single-bit numbers. And you can go on linking simple logic gates in greater and greater combinations to build a full-fledged computer that can perform a huge number of functions. Now, in the 50 years since Shannon and Stibitz, computers have evolved from automatic calculators into the most versatile machines ever designed. But they still work in essentially the same way, by acting on two valued functions. And now we can appreciate the secret of their flexibility. The zeros and ones in these functions can represent numbers, as we've seen, but they can also represent other kinds of information, text for word processing, elements of a picture, even musical notes. So computers owe their power to the fact that both logical functions and information can be represented in the binary code. Now that we're familiar with the binary system, let's see how it's actually used in a computer to process information. When we play a note on the Synclavier's keyboard, the computer inside automatically encodes the music into binary symbols. Every key has its own binary value beginning at 0. For instance, middle C on the Synclavier is key number 27, so it has the value 11011. The next lower C would be 15, and so on. Every note played is called a musical event, and the total composition is a binary list of the keys that were pressed.
So the Synclavier is a complete digital workstation that allows you to take a musical event or a sound effect and enter it into the computer, into this 200-track digital memory recorder. So here's a sequence that I've entered into the recorder, and let me play the tracks for you one at a time. First starting with the hi-hat cymbal, snare drum, bass drum, cowbell, triangle, conga drums, and then we add the electric bass and then double the electric bass with the steel drums. Then we can come back to our directory of sounds and call up a set of vibes, for instance, and now I can record the vibes along with this prearranged track.
Fred can easily make changes in the composition by causing the computer to perform specific arithmetic operations on the coded numerical information.
Now we can instantly hear the vibes played back. We can speed that track up.
Tempo changes result from percentage calculations of the time duration between notes.
Slow it back down. We can transpose it.
To raise the melody one octave, for instance, the computer adds 12 to the binary value of the original notes.
And we could change instruments.
Each instrument is a string of binary values that represents its unique sound quality separate from the value of the notes.
And we can substitute the flute for that, playing the same notes and the same rhythms. And once all of this music has been entered into the computer via the keyboard or the terminal, it can then be printed out on a number of different kinds of printers to give you a hard copy on paper that you can then give to other musicians so that they can play the music that you have composed and arranged via the Synclavier.
Remember, none of the sounds just played came from a tape recorder. They were produced by synthesizers under the control of the Synclavier's computer. Instead of performing this score by interpreting the traditional music code, we're performing the whole piece on one instrument that's interpreting binary code. But the real marvel of encoding music on a computer is that we can produce sounds that just aren't available from conventional instruments. Let's say we want to perform a musical composition on a rather unorthodox instrument. the wine glass. Fred could create different notes or pitches by filling a whole series of glasses with different amounts of liquid. But learning to play all those notes quickly and accurately can take a long time to master. Fred is already an accomplished keyboard player, and we can take advantage of his skill because the computer can store and manipulate the sound of a single wine glass. Once it's in memory, the computer can calculate the sound that a wine glass would make at every pitch. That's possible because the computer encodes the sound in binary form. But how do we get from this to a binary number? With a microphone and a display scope, it's possible to represent sound graphically. The sound is produced by running my finger along the rim of the glass, which causes it to vibrate. These vibrations travel as waves into the surrounding air. When they reach the microphone, the waves create a tiny current, a varying voltage that makes the picture on the scope. The electrical signal varies in the same way as the sound signal. You could say that the two are analogous to each other. For that reason, we call this picture an analog representation of the information. We've said that we'll encode this information with binary numbers. But just what information do we have here? The vertical axis represents the volume of sound, displayed as the amplitude of a sound wave. The pitch of a sound depends on its frequency, the rate at which the wave rises and falls over time. We can read frequency against the horizontal axis, which indicates time. There's something else the analog picture can tell us. Each instrument has a unique voice, what musicians call timbre. The characteristics of an instrument show up in the waveform picture. Here's the waveform of a flute, for example, which is smooth. Now a violin, playing exactly the same pitch at the same volume. We can see that the waveform is jagged and rough. Our wine glass has yet a different waveform pattern, conforming to its unique sound properties. We want to convert this analog signal into a series of numerical values using the binary digit code. This process of analog to digital conversion has become increasingly important in recent years. It has other applications in audio systems, such as compact discs. And picture information is converted to digital for transmission from spacecraft and in many computerized video effects. Converting from analog to digital is a bit like changing a ramp into a staircase. We want to limit the infinite number of possible heights along this analog ramp to a finite number of digital steps. The sound waves from our wine glass are like the ramp. They have continuously varying levels. If we convert the wave into steps and assign each one a binary value according to its volume, we can store a representation of the sound wave in the computer's memory. Of course, we want to use computer memory and processing time as efficiently as possible, so we create as few binary steps as possible. But too few steps won't distinguish enough different volume levels. The synclavier divides the possible range of volumes into 2 to the 16th steps. So for this amplitude, say, or this amplitude, we send to memory a 16-digit binary number corresponding to the closest step. Even though the representation isn't exact, with over 65,000 steps, human ears can't hear the difference. But how often should we send a binary value to memory? There are an infinite number of moments in even the shortest sound. We can do with time what we did with volume, divide it into a finite number of steps. This is called sampling, and it means that a binary representation of the sound volume is sent to memory only at specific time intervals. The minimal rate for sampling was determined in the 1920s by Harry Nyquist, a mathematician at Bell Labs. He proved that if sampling occurs at twice the highest frequency in the signal can be represented perfectly. At that rate, the digital sample preserves all the tiny irregularities in the waveform that give each instrument its unique timbre. Given the limits of human hearing, it's sufficient for the synclavier to take approximately 50,000 samples per second. Now that we've sampled the sound of a wine glass, the synclavier can process this digital information through its own stored programs to fill out the entire range of wine glass pitches. And that means we're now ready to hear a composition in a way not possible before. But first, we need a melody. The pattern of holes and no holes on a player piano roll is itself a digital code. And since it's already based on just 2 symbols, it's easily converted to the binary code of a computer. The QRS company produces its player piano rolls in 2 forms. the paper ones we've already seen, and floppy disk versions for home computer use. We've connected this personal computer to an inexpensive synthesizer. Not bad, eh? But thanks to similar digital coding schemes, this computer can also talk to the synclavier. So now, Scott Joplin, as he would have sounded playing the wine glass. We began with a code created long ago, the musical score. Like all codes, a system composed of symbols and rules of interpretation. Then we translated that code into a machine-readable form, the mechanical process made possible by a player piano roll. Now we've seen that the binary code enables a computer to store, manipulate, and play back the musical information. Thanks to the simplicity of binary arithmetic and the logic circuits that are based on it, almost any kind of information we can imagine can be processed by a digital computer. Modern computers, in all their dazzling power and variety, are based in a very real sense on a simple numerical code with just two symbols.